So, basically, I just wanted to take a second here today to do another attempt at converting a decimal number into IEEE floating point. I know the review session was a little rough, so I just kind of wanted to take a second here to do it in a slightly more streamlined and condensed manner for your studying pleasure. So, what I want to do is I want to start by taking a standard decimal number. In this case, it'll be 313.5625. And I want to convert this number into IEEE floating point. Now, a quick reminder about IEEE floating point. IEEE floating point is defined as the following. It is a single bit for the sign, right? The sign bit indicating whether the number is positive or negative. There are 8 bits for what we call the exponent to store the value of the exponent, which we'll see in a minute. And there are the remaining 23 bits for the fractional component of our number. The formula for this calculation is as such. The underlying number that we want to represent can be represented as n equals 1, -1 times s, our sign bit, times 1 point, our fraction, times 2 to the exponent minus 127. Okay, so that's the formula. Now, what I'm going to do is we're not going to start with this formula. We're going to kind of break it down to get to the pieces we need to make this formula. Because this formula is what's used to take the stored IEEE floating point value and convert it back into a standard binary number. Okay? So, if we have our decimal number, the first thing we need to do is convert this decimal number into a binary number. And really, we can think of this as being 2 parts. The first part is we need to convert what is to the right of the decimal place into binary. The second part is converting what is to the left of the decimal place to binary. Now, I'm going to do the right of the decimal place first here, even though it can be left or right. It doesn't really matter the order in this specific case. So, if I want to convert a fractional decimal number into a fractional binary number, the algorithm is as follows. We are going to take the actual number in decimal, and what we are going to do is we are going to multiply it by a value of 2. So if we multiply this by a value of 2, the result we're going to get back is going to be 1.125. Now, after we do this multiplication, we check, is the resulting value greater than or less than 1? In this case, it is greater than 1, so that means we make the immediate bit afterwards a 1. And then we are going to subtract 1 from the left side of the equation. Again, the lecture slides show the more mathematically formal process, so for the sticklers in the audience, we are technically subtracting 1 from both sides, but I'm just going to say I'm subtracting it from the left because that's what it looks like visually in this example. But I promise you the mathematics do in fact check out. Anyway, now that we've done this, and we've subtracted 1 from the left side, we are going to multiply by 2 once more. 1.25 multiplied by 2 is 0.25. Now, because this resulting value that we got after multiplying by 2 is still less than 1, the next bit in sequence is going to be a 0. And because the left side of the equation is still less than 1, we're going to multiply it by 2. So 0.25 times 2 is 5. Now, 0.5 is less than 1, so that means the resulting bit we add here is another 0. And then we're going to do this multiplication one more time. We're going to multiply 0.5 by 1, which just gets us a result of 1.0. And because this resulting value is greater than, or in this case equal to 1, we're going to add a 1 as the next digit. Now, normally we would subtract 1 from the left side, but now we have 0. And when you have 0 on the left side, you're done. So what that is telling us is that 0.5625 in decimal is 0.1001 in binary. Okay? So that is the first part of our equation, our solution. We can convert the second part of this to binary, 1001. Now we have to go and convert the first part, the left side of the decimal point. We need to convert 313 into binary. So the way I'm going to do this is I'm going to do this the lazy way. You can build out, right? 1, 2, 4, 8, 16, 32, 64, 128, and in this case, 256. I know it has to be up to 256 because the value is 313. And you can kind of play around with this a little bit, but the idea is you want the largest number you can to be used to store. So I know I want 256 here because the number itself being stored is greater than 256. So I know that if I put a 1 here, that means we have 256. Now what I need to do is I need to mark 1 on all the numeric values that sum up to 313. So here, if I want to do a little mathematics, right, if I want to do some addition, normally I do this on a calculator, but I'll do it here for your viewing pleasure. So if I have, say, 313, I want to, say, subtract 256. So that's 313 minus 256, and that gets us 57. So that means we still have 57, unit number. We need to basically make 57 with the remaining values. Now 57 is less than 128, so that's not helpful. It's less than 64, so that's not helpful. It's supposed to be a 2. But 57 is greater than 32. So what I can do, and I'm going to move this out of the way, is I can do 57 minus 32. 57 minus 32 is 25. So that's going to give us a 1 in the 32's place. And then we're going to go to the next digit. And we're going to ask ourselves, okay, is 25 greater than 16? It is. So I'm going to subtract 16 down here, which gets me 9. And we're going to take a mark here. And now, is 9 greater than 8? Yes, it is. So that gets us a 1 left over, and we're going to mark a 1 here. Now, 4 is not less than 1. 2 is not less than 1. But 1 is equal to 1, so we'll put that here. So we've converted our number. And I can check my work by summing these values, right? If I sum 256 with 32, with 16, with 8, with 1, that's going to result in a value of 313. Okay. So I can come over here and I can say that this result, I can't undo. Whoopsies. This resulting binary string is going to be the left of the binary point. So that is going to be 100111001. So that is our converted number. So 313.5625 converted to binary is 100111001.1001. Okay, so that's like step 1. So we still need to do some conversions in order to actually make this a proper IEEE number. Now, we need to store a sign bit, we need to store an exponent as 8 bits, and we need to store a fractional component as 23 bits. Now, the way IEEE works is that we take our binary fractional number that we just created and we quote-unquote normalize it. What normalization means is that we make it so that the number starts as 1 point something. So currently ours is 100111001 point, right? There's a couple of digits between the first one and the binary point. Now, this is what we want to change. So we want to normalize this number by moving the decimal place over so that the binary point comes after the first one, and there is only a single digit to the left of that binary point. The reason we do this, by the way, is it allows us to only store the fractional part of the number and just assume the non-fractional, the integer, the whole part of the number, as just always being 1, and that makes it easier because there's less information to store. Okay, so this normalization process. Really, in this case, the normalization process is just going to be moving the binary point over. In this case, 1, 2, 3, 4, 5, 6, 7, 8 spots. So to rewrite that, we would write it as 1 point, oh come on, there we go, 0, 0, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, times 2 to the 8. Now, it's 2 to the 8 because we moved the decimal places 8 spots to the left. And if I apply 2 to the 8, it would move this binary point 8 slots back to give us back our original number. Now, this is now normalized. We have 1 point and a fractional component down here. This whole thing is fractional. And we know our exponent is 8. Okay. Now we are almost done here. It turns out that that's the fractional component right there. That is the raw binary that we're going to be storing as IEEE number. We know the sign bit is going to be 0 just because this is a positive number. The only thing we have yet to calculate in final calculate is the 8 bits that make up the exponent. Now we know in order to take this normalized number and get it back to the original value, we need to do 2 to the power of 8. Now, you might think that that means we store 8 as binary, but that is in fact incorrect. If we look over to the equation in the top right-hand corner of the screen, we'll recall that the way the information is expected to be stored is that the stored exponent value will be subtracted. We'll subtract 127 from the stored exponent value, and then that will be what 2 is raised to, the power that 2 is raised to. So if we're going to take the stored exponent value and subtract 127, we need the result of that operation to be 8. So we're not going to be able to store 8. We're going to be storing whatever number minus 127 gets us 8. Okay? And I can write that as a basic algebraic equation. Okay? I can say that 8 equals exponent minus 127. All right? And if I solve by adding 127 to both sides, we get 135 equals exponent. Now, that means that we want the exponent value we store to be 135. But that's still in decimal, and we're going to need to make that binary. So very quickly, I will 128, 64, 32, 16, 8, 4, 2, and 1. And I can do the same thing I did previously. I know that, 135 minus 128 is going to be 7. So that means 7 is less than 64, less than 32, less than 16. It's less than 8. Now, I could do the rest of the math, but I'm just going to quickly shortcut. 4 plus 2 plus 1 is 7. So in order to make 7, we need all 3 of those bits. And that, right there, is the value 135 in binary. And on top of that, this number is the exponent value, the 8 bits of exponent, that we are going to be storing inside of the final IEEE floating point number. Okay? So, to finalize this, to round this out, we will write out our number. And I'm going to give myself a little space for our final answer. Okay. So our final answer, it's first going to be the sign bit, which is going to be 0. And then it's going to be the exponent. These 8 bits we just calculated right here, those go next. So that's going to be 1, 4 zeros, and 3 ones. And then it's going to be our fractional component coming in third. So that's going to be 0, 0, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1. And that is going to be our final IEEE number, where we have the sign, the exponent, and the fractional component. And I'm putting the spacing there for convenience, but this is just a single 32-bit bit string that gets saved. And that's it. We're done. We've done the conversion. And now the nice thing is if you need to go the other direction, right, I'm going to try to do this in a reasonable amount of space, so apologies if this gets a little unruly. But basically, if we want to go backwards, right, if we are given a IEEE floating point number and we want to convert that into a decimal value, well then we are going to apply the formula that we were given. And we're going to actually just put the numbers into this formula. So that's going to give us -1 times 0 times 1 point times 2 to the, I'm going to just write this out as decimal just to make it sane, 2 to the 135 minus 127. Okay. So that is going to be the ultimate calculation we do. We know that 135 minus 127 is 8, but if we didn't, we would do that mathematics. And so we know that 1 times 0 is 0. So that's going to give us a normalized number. So that's going to give us 1 point which if we apply is going to give us which is the original decimal that we started with. And then it's just a matter of converting these two numbers back into decimal values, which again we would do in much the similar fashion, right? So that would ultimately come back and give us our final result of 313.5625. Okay? And so that is, I think, a little bit more condensed, streamlined, and well-articulated example of the kind of process of converting from and then back to an IEEE floating point number. So, yeah, that's really it. That's all I wanted to say. I think that did the thing. So, thank you all so much for watching. And if you all have any questions about this, just hit me up on Discord or via email. And best of luck on the exam. All right. Thanks, y'all. Bye.